All right, time to do some practice using the chain rule. One of the most important and fun rules. And you want to do lots and lots of practice with this rule because you want it to be totally second nature. You want to be able to spot when to use the rule. Spoiler, function in a function. And then you want to be able to apply it so quickly and efficiently that it's second nature. You don't even have to put a lot of thought into it because then you can think about the more interesting parts of calculus which are to come. As always, when you're doing your practice, do as much as you can on your own first before watching these videos. And if you need to watch the video step you get unstuck, make frequent use of that pause button. Only go to the point where you're like, I don't know what to do. And then once you figure out, now I have an idea, pause and do the rest of it by yourself. And then you can watch these as sort of like, alternative perspectives. All right, well, let's get into it. So we're going to find the derivative on our first problem of two functions. Now, if you stare at these functions, here you have e raised to the power 31x. And here you have e to the x raised to the power 31. Now, what do you notice? Well, you might notice that, lo and behold, these are the same. In other words, at the end of the day, they're the exact same function. So what should be true? Well, they should have the exact same derivative. So we're going to do the derivative twice, and we better get our answers to match. Now, at this point, you might be wondering, well, why are we doing it twice? What's the point? Well, there's actually a slightly different thing going on here. So let's start with our first one. So we're looking for the derivative of e to the 31x. So we see a function in a function. Which layer is the inside function and which layer is the outside function? Well, the inside function, that's not so hard to spot. That's the 31x. That's what's on the inside. So what's the outside function? Well, once you spot your once you've spotted your inside function, almost tripped up there, then what you do to figure out what the outside function is to say, well, 31x is like what's on the inside, so replace the 31x by, just your variable name. So we're used to x, we can call it whatever variable you want. So it's really the function e to the x, except instead of x, we've plugged 31x. So the outside function is e to the x, so this is the function on the outside, and the inside function is 31x. Okay, so according to the chain rule, take the derivative of the outside. Derivative of e to the x is e to the x. So oftentimes we'll say the derivative of e, which means the derivative of e to the x. So what do we have? Well, so the derivative of the outside is e to the something. The something is the inside, 31x, times the derivative of the inside, 31. Now normally we would write this, put the 31 in front. 31e to the 31x. All right. Now that's our first derivative. Let's go to our second variation, our second part of it. The derivative of e to the x raised to the power 31. Now, let's think about it. Now what's our inside function? Well, our inside function is the e to the x. Now you might notice here, the parentheses are really sort of the clues as to what's on the inside. Not everything uses parentheses, but you can kind of say, oh, would this be a natural place to put parentheses? If it is, that's like, maybe this is my inside function. Okay, so what's on the outside? We see that the e to the x is the inside. Well, the outside is like the function x to the power of 31. See, something to the 31 power. That's the outside. So, what's the rule? Well, take the derivative of the outside. So the derivative of the outside would be 31 comes down x to the 30th. So that's the derivative of x to the 31. So we're going to do something similar. 31 something to the 30th. Well, what's the something? The something is the inside, which is e to the x. Then we times it by the derivative of e to the x. The derivative of e to the x is e to the x because we're timesing by the derivative of the inside. Now, notice how much do we have? We have e to the 30x, e to the x, and so if we put that together, we'll have 30x plus x, or 31x. And lo and behold, they match. Well, they should match, because it shouldn't matter how we proceed. If there's multiple ways to express it, either way that gets us to the answer will always produce the same answer, because we're consistent. Once we follow the rules, we're always going to get to the right answer. This just shows that in some cases, there might be more than one way to follow the rules. All right, next problem. Find the derivative of x squared plus 3x squared in two different ways. First, we'll do it by expanding, and then by the chain rule. Okay? And then it says find the derivative of x squared plus 3x to the 100 using one of the two preceding methods. Well, let's start. So, first by expanding. So what does that mean? Well, it says if I want to take the derivative of x squared plus 3x quantity squared, that's really the same as the derivative of x squared plus 3x times x squared plus 3x. All right, so now we do our foiling. X squared times x squared is x to the fourth. X squared times 3x, that would be 3x cubed. And then there's another 3x cubed from the inside terms. So that would become 6x cubed. And then the last terms, 3x times 3x, 9x squared. Okay, so now we've expanded. Haven't taken a derivative yet. We've just rewritten what we're taking the derivative of. And what we get, well, now we have a sum, so we take the derivative of each piece. Derivative of x to the fourth is 4x cubed. Derivative of 6x cubed, 18x squared. Derivative of 9x squared, 18x. Because remember, powers come down and multiply, and then you decrease the powers by 1. So like the 3 comes down, 3 times 6 is 18, and then 3 goes to 2, 2 comes down, 9 times 2 is 18, 2 goes to 1. Okay, well that's all good. Now, that would be if we expanded. Now, what if we were to do the chain rule? How would that work? Well, we would say the derivative of x squared plus 3x quantity squared. Now we have to think about what's happening. What's on the inside? What's on the outside? Well, the inside, again, we can sort of see parentheses giving it away. This is the inside, the x squared plus 3x. What's the outside? Well, the outside, okay, if x squared plus 3x is my inside, imagine calling that my variable. So it's something squared. So really my outer layer is the square function. So I could say my outer function, I could call it x squared, but really I can use any symbol I want. And if the x confuses you, use a different symbol. So according to the chain rule, take the derivative of the outside. Derivative of the outside, derivative of something squared, the 2 comes down. So the 2 comes down to something to the 1. So we have 2 something to the 1. See, normally it would be like derivative of x squared is 2x, but it's not x, because we're going to put our inside in. The inside is the x squared plus 3x. That's what goes here. Okay, and now we multiply that by the derivative of the inside. Well, the derivative of x squared plus 3x is 2x plus 3. Now, suppose we take a minute and expand. 2 times x squared times 2x would be 4x cubed. 2 times x squared times 3 would be 6x squared. 2 times 3x times 2x would be 12x squared. 2 times 3x times 3 would be 18x, which is 4x cubed plus 18x squared plus 18x. And you'll notice you get the same answer, which is not surprising because, again, we're taking the derivative of the same function. We're just approaching the derivative in one of two different ways. Now, the second part of this question. We want to find the derivative of x squared plus 3x to the 100. And so the question is, well, how do we do it? Well, we could expand like we did here and then take that derivative, or we could do the chain rule. I think the chain rule is the better option because maybe you can do x squared plus 3x squared, but x squared plus 3x is 100 would be like, it's just so gigantic, and the numbers involved are just, and it'll take forever. But if we see what's going on, we say, oh, this is not so bad. We have our inside function, that's our x squared plus 3x, still what's on the inside. And then our outer function would be what? Well, our outer function would be something to the 100. So, x to the 100. So, something to the 100, I know how to take the derivative of that. So that's 100 something to the 99. And then, what's the something? Well, the inside, x squared plus 3x, times by the root of the inside, which is 2x plus 3. And now, that's the derivative. And we'll just, there we go. There's our answer. So he doesn't say you have to simplify, just says you have to find the derivative, and we found it. It's right there, ready for us to figure out. Beautiful stuff. All right, good. So this is just a demonstration that, yeah, sure, there are some options for small cases, but it's really good to understand the power of the chain rule because it makes some derivatives really quite easy to do. That's what we want. We want things to be easy. Well, that's why we're taking calculus, right? Make life easy. All right, so this problem. Use the Leibniz chain rule notation on y equals e to the cosine of x squared to find dy dx. All right, well, how would this work? Well, what we need to do is sort of figure out what's happening with this function. So the Leibniz notation is sort of you introduce intermediate variable names to sort of piece it together so that each layer is a very simple function. So suppose we start. So we have e to the cosine of x squared. So what do we have? Well, we really have layers here. Layers within layers within layers. So the innermost layer is the x squared function. All right, and then what's next? After that is the cosine of the innermost layer, and then it's the exponential. So this is 3 layers, functions within a function within a function. So what we'll start is we'll start here at the bottom. So we just have to come up with variable names. Let's say we say u is our x squared. So this is the innermost function. Now, what comes next? Well, now I say, what's my next layer, right? So my next layer is cosine of x squared. So that's going to be cosine of u, because my bottom layer at the very end is x squared. So that's not my variable, so I'm going to call that, let's call it v. Now, what comes next? Well, cosine of x squared, so that would be this bottom layer here, see, because u becomes x squared, and now that's being plugged into the e function, so this is e to the v, and now there's my function y. So I get that y is a function of v, and v is a function of u, and u is a function of x, as specified here. So really at every stage, we can write off to the side exactly what the relationships are. So we could say, well, y is e to the v, v is cosine of u, u is x squared. Now, how do you use the Leibniz notation? Well, what we do is for every step, there's a change. We say, okay, if I want to find dy dx, what we do is we combine all our changes. There's a change in y with respect to v, so dy dv. There's a change in v with respect to u, dv du. There's a change in u with respect to x, du dx. and we multiply these all together. So at every step in this chain, there are always simple functions. So look at it, derivative of y with respect to v. Well, this is the exponential function, so this would be e to the v. Derivative of v with respect to u, well, now it's the derivative of cosine with respect to u. Derivative of cosine is negative sine. Derivative of u with respect to x, well, now again, it's a polynomial, x squared, so that would be 2x. Okay, and now what you can do is you can say, all right, that is the derivative. Suppose you want it all in terms of x, now you start substituting. So for instance, here, with a u, I can replace u by what it is. U is x squared. How about the v? Well, that's really cosine of u, but I can replace what u is, so that's cosine of x squared. So what we get is, this is e to the cosine of x squared times negative sine of x squared times 2x. And other than rearranging, so some people might, for example, like to pull out the negative and the 2 in the front, but other than rearranging, that's our derivative. Now, as far as Leibniz notation goes, we tend not to explicitly write it all out because it's easier just to sort of follow through mentally what's happening. It's like, okay, what are my layers? Okay, I'm on this layer. Here's the rule for taking that derivative. What do I plug in? But if you want to work it all out, you can. Generally speaking, I don't, unless I'm specifically asked, because we're doing it all mentally. It's all happening mentally. If you're having a hard time doing it mentally, go ahead and do it on a couple problems until you get the hang of it. But once you get the hang of it, it'll become very natural, and then it's like, oh, this is good stuff. It's wonderful. All right. Well, let's try another problem. Okay. Find the tangent line to y equals e to the power x to the fourth minus x at x equals 1. All right, good. So now we're getting into saying, oh, hey, it's not just pure chain rule problem. There's a chain rule problem being involved in solving something. So it's after a tangent line. So we know for after a tangent line, we really are saying, well, we need to know a point and we need to know a slope. And so that's really, whenever asked for a line, we always say, okay, there's a point and a slope. So the point, that's almost always the easy one. We know the x-coordinate is 1. What's the y-coordinate? Well, plug 1 in. 1 to the fourth minus 1 is 0. E to the 0 is 1. Ha ha! Nice. Okay, so now we come to the slope. And the slope is almost always the more interesting part. One way to say more interesting, of course, is more fun. Because shouldn't we have fun if we're doing some calculus? So the way we find slope, that's our rate of change, it's our derivative. So we start by our derivative. So looking at our function, we can see if our function here, I'll write it down again, e to the x to the fourth minus x. See, if I put some parentheses here, it can really emphasize what's going on. The x to the fourth minus x is an inside function, and where is it inside? It's inside e to the, see, it's e to the x to the fourth minus x. So now I say, all right, so if I'm taking my derivative, working from the outside in, derivative of e to something is e to something. So I'll have e to the, and now the something is the same thing as before, because you leave the inside alone. E to the same inside. So x to the fourth minus x. Remember, this derivative of e to the x is e to the x. So there is a derivative shortening up here. It doesn't feel like it. Times on the outside. So I'll just emphasize at the outside. The derivative of x to the fourth minus x. Well, derivative of x to the fourth minus x, that's a polynomial. And that really says, take the derivative of each term by term. The 4 comes down, 4x cubed. Derivative of x is 1. Okay, so there's my derivative for any value of x, not my slope, because remember, slopes are numbers, they're not functions. This is a function. To get a number, we need to now plug in 1. So we can write this as y prime of 1. or if you like, y prime with a vertical bar at x equals 1. So that'll be e to the 1 minus 1, which is 0, times by 4 times 1 cubed, which is 4, minus 1, which makes that 1 times 3, which is 3. So our slope is 3. Good. So we've now found our point. We've now found our slope. So the last thing for us to do is to write down our answer. I like that part. So y minus our y value is equal to our slope, x minus our x value. And we can rewrite that as y equals 3x. Now, here we have a minus 3. Then we're going to add 1, right? Because minus 3, this minus 1 comes across as a plus 1. So that would become minus 2. So y equals 3x minus 2. That's our tangent line to the function e to the power x to the fourth minus x at x equals 1. All right, good. Now, on to the next problem. Okay, so we're given that y equals 4x minus 6 is tangent to y equals f of x at x equals 2. All right, so that's what we have. And now we're going to find the tangent lines to the following functions at x equals 2. Oh, so we're going to find a bunch of these. So really we have not one problem, we're going to do 3 problems. So we've got the y equals f of x squared minus x, we have the y equals f of x squared, and then we have the y equals f of x. Okay, so we're going to find 3 tangent lines. So let's just make a note, a recall. So recall, there's a sort of basic philosophy, and this problem is going to guide us here. So that is, if I have the tangent line at x equals a, what I really have is my function at a and the derivative at a. And of course, vice versa. Tangent lines are storing information about a function, specifically what's the value of the function, what's the rate of change of the function. And I can jump back and forth. So let's do that with our specific case. We know our value for a is 2. It's right there. So what is f of 2? So f of 2, to figure that out, we plug 2 into here. 2 times 4 is 8, subtract 6 is 2. So in other words, if I plug 2 in, I get 2 out. What is f prime of 2? Well, f prime of 2 is the slope. So f prime of 2 is 4. Now on a side note, we'll go ahead and just do a quick point out here. Another way to think about finding the derivative is you can actually take the derivative of a line, and the derivative of a line is the slope. So that the derivative of the tangent line is, of course, matching the derivative of the function. So another way to think about tangent lines, it's like, well, I'm going to match the function and the first derivative at the point. So that's how it's sort of the best flat line approximation, is that it's matching those 2 aspects of the function. That's going to be an important idea, especially when we get in towards the last part of Calculus 2. I know that's a long ways away, but start those planning those ideas now. Okay, so let's start with number 1. We have our new function, y equals f of x squared minus x. So let's write down our derivative, y prime. So according to the chain rule, see, x squared minus x is the inside, f is the outside. So you take the derivative of the outside, leave the inside alone, times by the derivative of the inside. Now, we're going to do our next thing, which is we're going to say what happens at 2. So, what do we get? Well, here, when we plug in 2, we'll get 2 squared minus 2. Well, that's 4 minus 2, which is 2. So that's f of 2, which is 2. So it goes to the point 2, 2. So here's our point. What's our slope? Well, plug in 2. 2 squared minus 2 is 2. F prime of 2 is 4. So this will be 4 times, then 2 times 2 is 4 minus 1. Well, that's 3. 4 times 3, which is 12. So for part 1, we now know the point of the tangent line and the slope, because we figured out, what is the function at 2, what's the derivative of the function at 2, and therefore we could say y minus our y-coordinate is equal to our slope times x minus our x-coordinate. And if you rearrange, that becomes y equals 12x. Then this would be minus 24. Then you're going to add 2, so it'll be 12x minus 22. And that's the first one. Now the others are going to be similar, but we're still going to do the work because, of course, the more work we do, the more practice we get. The more practice we get, the better we become. And we're going to be great. Oh my goodness, people are going to just see us starting down, holding our head up high with our confidence in calculus, and they're going to be saying, that person, they are confident about their calculus. Just look at them. Ah, what a great day. Okay, all right, now, number 2. Okay, so here, what do we have? Well, we have f of x squared. So y equals f of x squared. So let's be careful. What's our inside function? In this case, it's the f of x. And then what happens is that we have f of x squared. So f of x squared. So our outside function is the squaring function. So that's going to be important to keep in mind. So let's take our derivative. So y prime would be the 2 times the inside to the 1, right? Because the derivative of x squared would be 2x to the 1. 2 comes down, and okay, so that's the derivative of the outside with the inside plugged in times by the derivative of the inside times by f prime of x. Okay, so now let's get our point and our slope. Our point, still x value is 2, plug in 2, f of 2 squared. F of 2 is 2, 2 squared makes our point 4, 2 comma 4. What's our slope? Well, slope would be 2 times f of 2 times f prime of 2. So 2 times 2 times 4. So what does that become? Becomes 16. Now we have our pieces in place. So y minus our y value is equal to our slope, x minus our x value. Or we could say y equals 16x. Then we're going to get minus 32, 16 times 2 minus 32, add 4. So minus 32, add 4 makes it minus 28. And there we go. That's the second one. All right, 2/3 done. One more to go. And of course we're going to do it. We've come so far, we're not just going to stop. All right, so the last one. We'll do number 3 here. So y equals f of x. You'll see here, what's our inside function? It's our function f. What's our outside function? It's also f. Okay, cool. All right, well, that's perfectly fine. So what is y prime? So take the derivative of the outside, f prime. Plug the inside in, f of x, times the derivative of the inside, f prime of x. Now, that's our y prime. So what's our point? Well, we know our x-coordinate is 2. So plug 2 in and work your way through. So f of 2 is 2. F of 2 is 2. So it's still 2 comma 2. What's our slope? Well, let's see here. F of 2 is 2. And then it's f prime of 2. And then here we have f prime of 2. So it's f prime of 2 times f prime of 2. So that's really 4 times 4, which gets us to 16. So it's the same slope, but of course it's a different point. So, different line. And here you can say, oh, it's the same point, different slope, different line. So these are all different. So y minus our y value is equal to our slope times x minus our x value. Or, what would we get? Y equals 16x. Then we have minus 32 plus 2 more makes that minus 30. And there we go. That's it. That's our answer. And woohoo! We did it! We did it! Ah! What a fun problem. We could have kept doing that one for hours. It's so fun. All right. Well, but we got to keep going. So, on to the next one. A particle moves. So now we have motion. So when we hear that word move, we start thinking, oh, okay, so we have things like derivative for velocity and so forth and so on. Okay, so particle moves. So that at time greater than or equal to 0, its position is given by t e to the minus t squared over 8. So there's questions. Determine the unique time where you have positive time when the velocity is 0. So that just sort of says, the particle is moving around. So the velocity 0 says at that moment it's sort of stalled out. It's not moving to the left and it's not moving to the right. It's just sort of like, So we're trying to find that moment. Well, okay. And then also determine the unique time when the acceleration is 0. Well, okay. I wonder why they keep emphasizing the word unique. Well, I don't know. Maybe we'll see. But that tells us we shouldn't find two answers. If we do find two answers, something is wrong because we were told this is going to be unique. Well, let's begin. So we're after velocity and we're after acceleration. So we're going to start by taking our derivatives. So we have our position, which is our function s of t, and that's t e to the minus t squared over 8. Now, what rules are we going to need to take this derivative? Well, we're going to need the chain rule, which is not a surprise because today is chain rule day, but that's not the only rule we need. See, we also have t times here, which means we need the product rule. So we're going to need multiple rules, and that's usually the standard thing that happens. Oftentimes you'll have many rules involved. No problems. We can handle that. All right, so our next layer, velocity, would be s prime, the first derivative. So let's do I'm going to do the product rule because the product rule is sort of the bigger rule. And the chain rule is going to come up in the process of working out the product rule. So take the derivative of the first, 1 times the second, e to the minus t squared over 8, plus the first t times the derivative of the second. Now, here, the derivative of the second, that's where the chain rule kicks in, because we have e to the minus t squared over 8. So the outer layer is e, and I say, okay, derivative of e to something, well, the derivative of the outside is e to something, so it's e to the inside stays the same, because we're plugging the inside function back in, times by the derivative of the inside function. Well, the derivative of the inside, that's a polynomial, and so we do what we do for polynomials. The exponent comes down, and so the 2 will come down, and there's an over 8, so what we'll end up with is minus t to the 1 over 4, because 2 over 8 goes into 4. Now we're going to need to take another derivative, so oftentimes I find it helpful to clean this up. Because if we're going to take another derivative, it's in our interest to make sure we have it in a nice way. Because right now it looks like there's 3 things multiplying, but really, see, these two are more or less the same thing. They're both polynomials. So if we multiply them out a little bit, we end up with minus t squared over 4 times e to the minus t squared over 8. Okay, good. So now let's go ahead and do acceleration. Because we do need acceleration, we could pause and say, hey, let's find the answer for when the velocity is 0. We'll do that in a moment. Okay, let's work on our acceleration. So, acceleration. Second derivative. All right, so we take the derivative of the first. So, chain rule. Well, it's the same thing we just did. E to the minus t squared over 8 times negative t over 4. Product rule here. So, minus derivative of the first. The 2 comes down, so 2t over 4, which we'll write that as t over 2. So that's the derivative of t squared over 4 times the second function, t squared over 8. And then, okay, let's be careful here. We want to say plus, right? Because that's the way we usually talk about the product rule. Notice there's a minus here. That minus will carry through. If you want, we could go ahead and put an extra set of parentheses. And you know I'm a big fan of parentheses. So I'm going to go ahead and do that. So derivative of the first times the second plus the first times the derivative of the second. Well, that's e to the minus t squared over 8. And then times that by minus t over 4. All right. Now, the important thing, of course, to remember is that minus carries through. So don't forget. See, this is a case where if you're not being careful, you would say, oh, that should be a plus sign. But remember, that minus carries through to both terms. So, yeah, we want to be careful. We don't want to lose any of our signs. Oh, that would be sad. That would be a terrible thing if that had happened. All right, so let's clean that up. Because, again, we're going to have to do something with it. It's not just find acceleration. It's find when acceleration has a certain property, which means we're going to want to do something with the acceleration function that we've just found. So let's see, we have a minus t over 4, e to the minus t squared over 8. And then here we'll have a minus t over 2, e to the minus t squared over 8. And then here, let's be careful with our signs. We have a minus, a plus, and a minus. So if we put all that together, we'll get a plus. Then here we have a t squared over 4, t over 4. So that would be a t cubed over 16, e to the minus t squared over 8. Okay, if we put these two pieces together, they both have t over 4, t over 2. And so we can combine. So t over 4, t over 2, both negative. So this becomes a minus 3t over 4, e to the minus t squared over 8, plus t cubed over 16, e to the minus t squared over 8. Okay? And let's pull stuff out. What do these terms have in common? Well, a couple of easy things to spot. They both have e to the minus t squared over 8. Yep, that was pretty easy. They both have powers of t. We pull out the lowest power. See, our choices are t or t cubed. T is obviously the lower of the two. And then the other thing is I don't like fractions left. So let's go ahead and pull out a fraction big enough to get rid of all the fractions. So there's an over 16 and over 4. So I'm going to pull out an over 16. And if we do all of that, what do we have left? Well, let's start with this second term here, because since it has the larger power of t, I've pulled out the over 16, the e to the minus t squared over 8. I pull out 1t, so that means I'm left with a t squared. I have the minus from here. I already grabbed the e to the minus t squared over 8 and the t. I don't have the 3, and now be careful. See, it's over 4, but I pulled out over 16. So, what comes next? Is it minus 3? No. What is it? It's going to be minus 12. And where does the 12 come from? Well, essentially, I'm off by a factor of 4 in the denominator. See, I want 16, but I only have 4. So I'd have to multiply by 4 downstairs, or I'd have to multiply by 4 upstairs. So that's where that comes from. All right. Now we're ready to start answering the questions. So let's look at this. Oh, actually, before we do that, I'm sorry. I got so excited. I want to do the same thing that we did here over here. So let's clean up our velocity by doing something similar. So I'm going to factor e to the minus t squared over 8 out over 4. And see, there's no power of t that's common. So, and if we do that, what are we left with? Well, we're left with 4 from the first term minus t squared. All right, so now we're ready. Okay, so velocity equals 0. When would that be? Well, we look at this expression. we say, well, this part, e to the minus t squared over 8, that definitely is never 0. So it really says, when does 4 minus t squared equal 0? That's when t squared equals 4. Well, there's two cases, right? Positive 2 and negative 2. But remember, positive time. So this occurs at time t equals positive 2. All right, how about acceleration? So when does acceleration equal 0? Well, again, we go through and say, okay, this part here, the e to the minus t squared over 8, is definitely not 0. And by the way, one of the things you want to do is factor things, because if we're setting this equal to 0, then one of the things had to be 0. So we say, look, e to something is never 0, so that's definitely not causing my 0-ness. This could be 0, but when does t equal 0? Well, it equals 0 when t equals 0. But we know that t, again, has to be positive, so that's not our answer. So it has to come from the t squared minus 12. Well, that would be when t squared equals 12, which equals what? Well, take the square root of 12. So that's at time t equals root 12. Now, if you wanted to, you could say, hey, 12 has a square in it. It's 4 times 3. So you could write this as 2 times square root of 3. But if you didn't, you'd still be okay. Because, that's the answer. And there you go. Good. Nice. Good times. Good times. Okay. So let's do another problem. So we're given the following information for f of x and g of x. We want to find h prime of 1, where h of x is f of g of x plus g of f of x. And it looks like a k. I think it's a kappa, but I'll go ahead and say k, because we're among friends here. K prime of 4, where k of x is f of x times g of x. All right, and what's our information? Well, we don't actually know the functions. Instead, we have this table here. So it's like, well, what do we do? So what's happening here is this is sort of showing us one of the ways that we can be given information about a function. See, sometimes we don't have the ability to understand a function directly, but we have pieces of data. So here, this is a case where it's like, well, we have some data about what f and g are doing and what f prime and g prime are doing at certain points. So if anything, this is really saying, do we understand how to use our rules for derivatives? And can we apply them? It's almost like testing our symbolic understanding of the process. So, well, let's work through it. So here's what we want. We want to find h prime of 1. So how do we do that? Well, if I want to find h prime of 1, what's our first step? Well, first step is, what is h prime of x? Because if I want to find h prime of 1, I could say, well, let me find h prime of x, then we'll plug 1 in. So, as a reminder, probably I should have given myself some space. H of x is f of g of x plus g of f of x, right? So h prime says, go through. Now there's a plus, which means we take this derivative, we take that derivative, and we just do them separately and then add the results together. Each one is a chain rule. So be careful here. F of g of x is different from g of f of x. So let's go through patiently. So on the first term, it's take the derivative of the outside, f prime. Leave the inside alone, pristine. Then times on the outside by the derivative of what was on the inside, g prime of x. Plus, next term, take the derivative of the inside, leave the inside alone. Sorry, take the derivative of the outside, leave the inside alone, because the outside is g, so g prime, leave the inside alone, f of x, times by the derivative of the inside, f prime of x. Now, that's the symbolic thing. So how does h prime of 1? Well, that's f prime of g of 1 times g prime of 1 plus g prime of f of 1 times f prime of 1. And now we start using our table to unravel our onion type problem here. Okay, so let's begin. What is g of 1? See, I can't figure out what f prime of g of 1 is, but this is a case where oftentimes when we're doing derivatives, we work from the outside in. When we're doing the evaluations, we work from the inside out. So, what is g of 1? Well, we come up to our table and we say g at 1 is 2. So this part right here is 2. What is f prime of 2? F prime at 2 is 3. G prime of 1? Well, g prime of 1 is 7. All right. Okay, now come here. F at 1. F at 1 is 3. G prime of 3. G prime of 3 is negative 4. F prime of 1. F prime at 1 is 4. So that's 4. So, what do we get? We get 3 times 7, which is 21. And then we get minus 4 times 4, which is 16, minus, and therefore we end up with 5. And there you go. There you go. Nice. Cool. All right. Well, now we're going to do something similar for the other one. It's actually not a chain rule. It's a product rule. Well, it's still good to practice, right? So we're going to do the same process. We say, okay, look, here's our function, k or kappa. It's the product. And we say, all right, so if I want to find the derivative of this function at 4, first, let's write down what the derivative should be. So take the derivative of the first times the second plus the first times the derivative of the second. So plug in 4. So what do we get? That'll be f prime of 4. That's a terrible looking prime. So f prime of 4 times g of 4 plus f of 4 times g prime of 4. So we start reading that off. F prime at 4, 7. G at 4. G at 4, negative 3. F at 4, 5. G prime at 4, 1. So we have 7 times negative 3, which is negative 21. 5 times 1, which is 5. And if we put those together, we get negative 16. And there you go. So this is one of the ways you can deal with functions. You can say, well, maybe I have an explicit function, and then I take derivatives and I follow the rules. Or maybe I don't. But I have ways to combine my pieces together, and I have information about my individual pieces. But I can still figure stuff out, and I can still use the table. So it's learning to read the table. Learn to read the table and use what you have. All right, good. All right, now on to our next problem. So use y equals f of x shown below. So now we actually have the function, but instead of having an explicit formula, we say, here's a picture. All right. And we want to find a couple of derivatives. In fact, we want to find 3 derivatives. Oh my goodness. So we're going to find the derivative of f of x squared at x equals 2, f of x quantity squared at x equals 2, and f of x at x equals 2. All right, so we're after the derivatives here. Ah, good. Now, what's the moral here? Our moral here is we're going to try to figure out how to look at this picture and extract the information we need. Now, one thing that hopefully is clear when we look at this picture is that this is not just any function. It's what we would call a piecewise function where each piece is a line. So if you look here, locally, as a whole, it's not a line. But if I were to, cover pieces up, you say, well, look, what is this thing doing right here? And you say, well, it's a line, it's a flat thing. So that says that each piece is a nice flat thing. And therefore, it's easy to extract information about the derivatives locally. Now, where the 2 lines come together, that's where there's a broken part, like the absolute value kind of looking thing here. And that would be a place where the derivative is not defined. All right, so let's start with the following. So suppose we want to start with the derivative of f of x squared at x equals 2. Now, this says we're going to take the derivative of f of x squared, then we're going to plug in 2. So what do we have? Well, our inside function is x squared, our outside function is f. So we take the derivative of the outside, leave the inside alone, times that by the derivative of the inside, which is 2x. And then we're going to evaluate this at x equals 2. So derivative of the outside, leave the inside alone, times derivative of the inside. So what is that going to be? Well, that's going to be f prime of 2 squared, which is 4, times 2 times 2, which is 4. So now we come to our picture and we say, all right, what's happening at 4? So we come here and we say, at 4, we are a line. And we say, okay, well, what's the slope of the line? The slope of the line, this part that's going down, however that value is, that's the derivative. Well, what do we see? It's going downhill, so that's a negative slope. And we can even read off by following the squares. It's going down 2 over 1. So that says that the derivative at 4 is negative 2. So we have negative 2 times 4, which means that this is negative 8. And that's our answer for the first one. All right, well, let's do another one. Okay, so let's do the derivative of f of x quantity squared. Okay, now what do we have here? Well, we've sort of interchanged the roles of inside outside. See, previously the x squared was the inside, f was the outside. Now f is the inside, the square is the outside. Of course, when you change roles, you're going to change behavior most of the time. It's very unlikely that it's the same. And I should comment here that this is at x equals 2. It kind of, I will say it's kind of a fluke here. This comma makes it look like it's at 2 prime, but no, it's just a x equals 2 comma. It's an unfortunate looking comma. Okay, so we follow our rules. So we're going to take the derivative of f of x squared. The outside function is a square, so it's 2 f of x to the 1, because derivative of the outside with the inside plugged in, times the derivative of the inside. Then we're going to plug in x equals 2. So this would be, when we plug in 2 times f of 2 times f prime of 2. This is to the 1 power. That's not a derivative. That's to the 1. Okay, so let's go to the picture and ask, what does the picture tell us? Well, so we come to 2. So we come up here and we say, okay, what is f of 2? Well, we can read it off. So the function at 2 is 6. So this part here is 6. What is f prime of 2? Well, to figure that out, I say, what's the slope? Because again, I'm in a line segment here. Well, I'm going down 1 over 1. It's downhill, so it's negative. Down 1 over 1 means slope of negative 1. So we're going to have 2 times 6 times negative 1, meaning our answer is negative 12. All right, 2 down, 1 to go. All right, what's our last one? Our last derivative to take. Well, it's f of x. Okay, cool. So what do we have? So we're going to do the derivative of f of x at, and again, x equals 2. So according to this, take our derivative. The derivative of the outside, f prime, plug the inside in, f of x, times the derivative of the inside, f prime at x. And then evaluate that at x equals 2. So what is this? This is f prime of f of 2 times f prime of 2. So we get a little bit of an ununique type thing, right? F prime of f of 2. Okay, So let's figure this out. We know what f of 2 is because we did it in the previous one, right? F of 2 is 6. So this is f prime of 6. Then we also know what f prime of 2 is because, again, it's the slope times negative 1. So what we need to do is figure out what is f prime of 6. So we come over here. Here's 6. It's a line segment. So what's the slope? Well, it's over 1 up 2. So it's slope of positive 2. So this f prime of 6 is a positive 2. And therefore, we get negative 2 as the answer. Good. All right. Nice. Good. All right. Now, our last problem. Of course, it's not going to feel like one because we have multiple parts. But really what we're going to do is just do a practice. We got to get comfortable with this. And so if you can just go through and write these down without thinking, then you're good to go. In fact, these are going to be most of the rules that we're going to encounter as far as taking derivatives. So if you can go through all of these derivatives that we're going to do right now, and you're like, yeah, yep, I understand it, cool, no problems, life is good. You're ready. You're ready for the big time. So let's begin. All right, so there's not a lot of humming and hawing. We're just going to go through step by step. Now, our first one, well, plus means you can take the derivative of each piece. So you take the derivative of sine of x squared, work that out. Then you got to take the derivative of e to the cosine of x, work that out, and put them back together. So what do we end up with? Well, so for part A, we would have derivative of sine is cosine. So cosine of inside stays the same times the derivative of the inside, so times 2x, plus e to the cosine x. So the outside is e to the something, so derivative of e to the something is e to the same thing. So e inside stays the same, e to the cosine x, times the derivative of cosine, and the derivative of cosine is negative sine. Don't forget about the negative sign here. Ha 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 ha. See, negative sign? Yeah. All right. So times negative sine of x. All right. And we're done. Because we aren't asked to simplify, so we're not going to. All right. So that's A. Let's try B. Now, what's our big rule? What's our sort of first layer in our onion here? Well, the first layer is it's a division, so it's a quotient. So we can do a quotient rule. Now, by the way, I should point out now, there's another way for us to think about doing the quotient rule if you're someone who's morally opposed to doing quotient rules. And that's to make the sort of the following observation, is you could rewrite things like this in the form sine of root y plus y squared e to the y, the numerator, and then the denominator would become 2 plus cosine of y squared to the minus 1 power. And then what you can do is you can do a product rule, but on this part you would do a power rule. So there's power rules when you have something to a power. We'll do a quotient rule. All right, so part B. Well, so what does the quotient rule say? You can remember however you want. A lot of people say low d high minus high d low. If that helps you, that's fine. I usually start saying, well, you take the bottom. So that's 2 plus cosine y squared, just the bottom straight up, times the derivative of the top. Now, here we see that we're going to need to do a chain rule because we have sine of root y. And remember, when you see square root of y, if you're thinking calculus, what do? Well, you make it more calculus friendly. And how do you make square root of y more calculus friendly? Well, you say, hey, square root of y is really just another way of saying y to the 1/2 power. All right. And notice, by the way, we're taking the derivative with respect to y. We can take the derivative with respect to any variable we want. Any symbol can be our variable. we could put little smiley emojis and say, what's the derivative with respect to the smiley emoji of this expression? That's perfectly allowed. We would never do that, but it's perfectly allowed. Okay, all right, back to our business at hand. Okay, so here we're going to do each one individually. Derivative of sine is cosine. Leave the inside alone, y to the 1/2, times the derivative of the inside, which is 1/2 comes down, y to the -1/2. Okay, that's the first term. Plus, for y squared e to the y, what's the rule? It's product rule. So, derivative of the first, 2y times the second, plus the first, y squared, times the derivative of the second, e to the y. Okay, now believe it or not, that's not the full numerator. See, that's just the bottom times the derivative of the top. Now we need to subtract, and oh dear, I don't know if I have enough space. So, the high d low, right? So it's the top, so that's sine of root y plus y squared e to the y, all right, times the derivative of the bottom. Now, the good news is the bottom has an easier derivative. Derivative of cosine is negative sine, and the inside stays alone, but then we multiply by the derivative of the inside, which is 2y. All right, we squeezed it in, just barely, but barely still counts. Are we done? Oh, no, not with the quotient rule. All of that over the bottom term squared. And there we go. Now we're done. Now we're really done. Okay, so that's part B. Okay, so we made, we're halfway there. Okay, part C. Now, here we go. This one, it's actually mostly the power rule. But of course, there's one part that's a little bit tricky. And that's just a very unfortunate convention. You see this part where we have it to the 20th power? Of course, I've shaded it so much you probably can't even tell it says 20 anymore, but it does. It says 20. There's just a convention in trig to write the power sort of in an inconvenient spot. So let's try to write that in a slightly more convenient spot so we can actually see what's happening. So for part C, what we would have, if we were writing it, so if it was any function that wasn't a trig function, we'd write it in the following way. We would say, okay, we're looking for the derivative of, and then we're going to have this first layer, we're going to have 1 plus, and then we're going to have sine of 1 plus x squared to the 10th. And now, see, I'm plugging 1 plus x squared to the 10th into the sine, and then we're taking that to the 20th power, and this 1 plus this sine squared is the negative 50th power, and then I have a close parenthesis. So when we put the 20 here, normally we would put it there. All right. So, are you ready? If we were to follow the notation for the general power rule, so see here I have something to a power. So the rule says bring the something down. See this power comes down. So negative 50. Then the whole inside, 1 plus sine of 1 plus x squared, to the 10th. And then to the 20th. And now subtract 1 from the power. Okay, what's my new power? So it was negative 50 before. The new power is negative 51. Yeah, be careful here. Subtract 1. It doesn't just mean like make it 1 smaller in size. It means subtract 1. So it's not negative 49. Okay, now we're up to taking the derivative here. Now the good news is 1 plus, that derivative is 0, so that 1 plus goes away. So we're really going to focus on our next layer is really the sine, this something to the 20th. So something to the 20th, our next layer says the 20 comes down, right? The 20 comes down. The inside sine of 1 plus x squared to the 10th, and then to the 1 less. So this is to the 19th power. All right? Good. Now, we keep working our way in. What's our next layer? Well, our next layer is the sine function. So this will be times the cosine of, and then the inside stays alone because the derivative of sine is cosine. So cosine of 1 plus x squared to the 10th. And then, what's next? Now we're working our way in. 1 plus x squared to the 10th. So the 10 comes down. So 10 times 1 plus x squared to the 9th. And are we done? No, we're not yet. What's left for us to do? Times by the derivative of the inside. And the derivative of 1 plus x squared is 2x. Okay, good. So if you put that all together, that is our derivative. It's just patience. One layer at a time. Work your way through the onion. You can do this. You really can. I promise you, you can do this. I know you can. I know you can. All right. One more. Our last hurrah. And then we can take a breather for a few minutes, right? All right. So let's see. Let's pick a nice, good color. We'll go with green. Green's a nice, good color. Okay. So this one, sine of x plus e to the x times tangent of 1 over x squared plus x cubed e to the x squared. Now, there is one thing we should do before we start, which is we should make one of these things more calculus friendly. Now you're probably thinking, well, what's the thing that needs to be more calculus friendly? The answer is the 1 over x squared. What's the calculus friendly way to write 1 over x squared? It is as x to the minus 2. So we like to work with x to a power. So if it's 1 over something, we like to write it as like x to the minus something. If it's a square root, we put in a half, and so forth and so on. There is an exception when we get to what's known as integration, but we'll talk about that exception when we get there. So for now, when we talk about calculus friendly, we want to work with things to powers, because that way we have a nice power rule. Okay, so for our last one. All right, so we should have marked our previous one as this is what C is. And so for our last one, we have D. And here we go. We're going to work our way through. So our outside layer is the sine function. So the derivative of the outside is the cosine. Leave the inside alone. X plus e to the x tangent x to the minus 2 plus x cubed e to the x squared. Okay? So far, so good. Times by the derivative of the inside. So, derivative of the inside. Well, we have a plus, which means we need to take the derivative of the first and the derivative of the second, we add them together. Now, the nice news is the derivative of the first is straightforward. So, 1. I like the derivative of x. It feels good. Plus, now, e to the x times tangent, well, that means we need a product rule. So, product rule, derivative of the first, e to the x times the second. Tangent of x to the minus 2 plus x cubed e to the x squared. Okay, derivative of the first times the second plus the first times the derivative of the second. So, here we go. The second function, meaning this tangent of, now we have to do a chain rule. So, tangent of stuff. So, derivative of the outside, derivative of tangent is secant squared of, leave the inside alone, x to the negative 2 plus x cubed e to the x squared. But we're not done with this piece yet. So, now I've got to times it by the derivative of the inside. So, times by derivative of x to the negative 2. Well, negative 2, x to the negative 3, because the negative 2 comes down, x to the 1 less, plus, how about this one? Here we have x cubed times e to the x squared, so we need to use a product rule. So, derivative of the first, 3x squared times the second, plus the first times the derivative of the second. Well, there's another chain rule, e to the x squared. So it's the derivative of e is e, so e to the x squared times the derivative of the inside, which is 2x. Okay, and this part is the derivative of the inside here, which is attached to that. Now, are we done? And what are we missing? We actually are missing something. Can you see what we're missing? Oh, this is a good check for you. Can you see what we're missing? It's a parenthesis. Oh, how could we forget our parenthesis? Okay, all right. Whew. Wow, that's it. That's part D. Now, as you can see, you can have expressions which are, mind you, this is not the most elegant, but really there's layers within layers within layers going on here. Product rule, chain rule, sum rule, and you have to be careful here. And I think one of the hardest things is being careful about when you start getting all these rules put together, it can become confusing. It's like, wait, does this go with that? Does it not go? What's going on here? I'm losing track of things. And we don't want to get to that point. We never want to be in the stage. We want to be like, yeah. So that's good. So for instance, this piece right here is not attached to these terms because this is the derivative of the inside coming in from there. So that's an example of what I mean. So it's be patient, figure out what's attached to what, use your parentheses correctly, and of course, practice. I know you can do this. I know it's not easy when you start, but the more that you practice, the more natural these problems become, and after a while, you can make them second nature. So keep going. You're going to get it. You're going to get it. It'll happen. All right. Thanks for hanging in there. Have a good day.